Hello, everyone. I'm Lance. Today, my colleague Dennis and I will give a presentation on URB Excalibur, the new VMware full platform virtual machine escape. First, who are we? We are security research at an group that is a security lab, and we escaped from virtual machine many times. What's more, we won the Pony Award last year. This is a roadmap for our talk. First, I will share an introduction to VM Escape and VMware's hypervisor. In the second part, we will share a journey of VMware hypervisor's vulnerability discovery. The last part is about our efforts in the exploit development of VMware VM Escape, where we will share a new set of exploitation primitives and how we use them to develop exploits for all VMware's hypervisors. What is VM Escape and what are its dangers? VM Escape refers to an attacker launch an attack from inside a virtual machine using vulnerabilities in the hypervisor to escape and control the host. A company's cloud platform may run a large number of virtual machines and services on one host, which can cause significant harm. It can be said that VM Escape is one of the most catastrophic threats to the cloud. This diagram is taken from a paper VMware published many years ago. We can see VMware's hypervisor consists of three parts: VMX, VMM driver, and VMM. As for the virtual devices we are most concerned about, their code exists in VMM and VMX. Most part is in VMX. So, what are the attack surfaces of VMware's hypervisor? I have a list, a table, and almost all of the modules on it have had vulnerabilities in the past, even leading to VM escape. Except for the VMM. I believe that VMM may also have vulnerabilities, just like KVM, but the difficulty of finding vulnerabilities in VMM may be too high compared to the ones above. On the right side, I have listed all the publicly disclosed VM escape from 2021 to the present, not including the escape completed at Pontoon this year. It can be seen that in recent years, security researchers have mainly focused on researching USB attack surface. Now let me share how we start the journey of vulnerability discovery in VMware's hypervisor. Having already analyzed VMware's architecture, attack surface, and history vulnerabilities, we choose an interesting and potentially risky attack surface to focus on EHCI controller. To begin reserve engineering VMware's hypervisor, we needed an entry point. Researching for specific strings is a simple and effective way. By researching for EHCI in IDA, we can quickly locate the code for EHCI implementation. From there is a matter of understanding the EHCI specification, and the QEMU's code will reverse engineering VMware's code. First, I need to take a few slides to introduce the EHCI and the USB 2 controller. The diagram on this slide is taken from the EHCI specification. From this diagram, we can see that the EHCI specification is responsible for the communication protocol between the system software and the USB controller. The USB controller then converts the data into USB 2 packets to communicate with the USB device connect to it. Therefore, during the reverse engineering process, we focus on understanding how EHCI commands and data packets are handled by VMware's code and converted into USB data packets to be sent to the USB device. The slide introduces the basic data structure of EHCI packets and the state machine of the EHCI controller. We can see that EHCI consists of QH and QTD, along with their structure, like ITD. But today, we will focus on only QTD. QH stands for Q head, which forms a singularly linked list. Each QH carries a linked list of QTDs, and the QTD is the smallest structure in EHCI data transfer. The QTD has a buffer pointer array, where buffer pointer stores physical memory address. From the diagram on the right, we can see that USB controller first passes the QH, then process and transfers the QTDs within the QH. When the transfer is complete, it checks if there are any QTDs that need to be written back. Afterwards, it moves on to the next QH and continues this loop. Finally, there is one more slide. We need to know what EHCI data transfer looks like. A USB device will have multiple endpoints for transmission, and each endpoint will have a unique pipe. The control pipe is used to configure the USB device. And it is present on every USB device. Then there are 3 tokens for QTD: setup, in, and out. Among them, the setup QTD is responsible for describing the entire transfer queue. Ultimately, a transfer queue will look like the diagram on the right, with the setup QTD followed by many in QTDs and out QTDs. Here, I show the execution flow of QEMU and VMware. We can see the difference in how they handle EHCI data transfers. QEMU processes each QTD as a single unit, treating each QTD as a packet. Depending on the token type, setup packets will execute do token setup, while in packets will execute do token in. On the other hand, VMware treats an entire EHCI transfer queue as a whole. It considers the entire queue as a single URB, and then submits the URB to the USB device by URB submit function. Data transfer and processing are likely to have vulnerabilities. For example, the well-known CVE 2020-14364 in QEMU occurs in the handling of each packet type. So, could there be bugs in VMware function EHCI control transfer, which also process data? The answer is yes. We discovered a critical vulnerability here and accomplished a series of interesting things through it. The vulnerability we discovered is CVE 2022-31705, which is a heap out-of-bounds write that affects VMware EHCI workstation and function, affects all of VMware's hypervisors. VMware assigned this vulnerability a score of 9.3. The code on the right is the EHCI control transfer function. I need to note that since VMware's hypervisor is a closed source software, their symbols, including function name, are named by ourselves. In EHCI control transfer, there is a loop that passes all QTDs in the QH and processes them based on the QTD token type. Further, for the setup QTD, which is the beginning of transfer queue, VMware will allocate a new URB. The size of URB depends on the setup length filed in setup QTD, which represents the total length of data to be transferred in the queue. Next are the out QTD and in QTD. We can see that when processing the out QTD, there is a check to see if the T bytes is an illegal value. T bytes is a member of QTD used to indicate the length of the data carried by the QTD. Setup length here represents the remaining length that the current URB can transfer. If T bytes is greater than setup length, VMware will only transfer the length of setup length. We can see that finally the EHCI read TD buffer data is read from the physical address carried by the QTD and returns the PURB data cursor point of the URB. The process then continues, subtracting T bytes from setup length to update the remaining transfer length. After processing, it will enter the next QTD process and pass the next QTD. The in QTD is similar, but since the direction of the in QTD is from the USB device to the system software, at this stage, the USB device has not received and processed this packet. So they won't have any data for us to transform. In EHCI control transfer, it will directly execute the next operation. So now the question is, where is the bug? We can see that in the processing of out QTD, there is a check for T bytes, which ensures that there will be no issue when setup length is subtracted by T bytes. However, when processing in QTD, there are no checks at all. The code directly subtracts T bytes from setup length, which means that if setup length is smaller than T bytes, setup length will become a negative number after processing this QTD. It causes an integer overflow. Now that we know there is an integer overflow bug when processing in QTD in this code, let's see how to upgrade this ability. When setup length is negative, it can't pass the check during out QTD processing. We need the setup length to be a positive number, which is easy. We just need to set up a large number of in QTDs, each with a T bytes value of 0x7FFF. The blue part below shows the value of setup length at each stage. Finally, we can subtract setup length to a large integer. At this point, setup setup length will be much larger than size of URB. We can append a out QDD with a size larger than the URB's data size at end, which can pass the code check, thus leading to a heap out-of-bound write. This is a vulnerability we discovered. In addition to CVE 2022-31705, we discovered a new other bugs, such as out-of-bounds read, information disclosure, which have all been fixed. We will give 2 examples here. First, there is an out-of-bound read vulnerability caused by pipe type confusion. We can choose a control pipe in the process and should handle isochronous pipe. Although their data structure are the same, they are used differently, which leads to problem. We can see the image in the right showing that during the transfer process of isochronous endpoint, the URB will have multiple packets, and the PURB cursor will be increased. However, a control pipe URB will not have multiple packets, so the current packet have actually already point to the data. When the URB's number of packets is 0, this won't directly cause a problem. But the issue is that the number of packets of control types URB is always 1, which means this code block will be always entered automatically, causing PURB data cursor to be increased beyond the range of URB, resulting in an out-of-bound read. Another one is an information disclosure vulnerability that exists in multi-virtual USB devices, such as USB audio, USB video, USB RNG. The cause of vulnerability is that when creating a new URB, VMware didn't use calloc or perform the memory set function on the URB data array. This leads to the data array carrying memory information. Many virtual devices will set write-back length to data length by default, which allow all this information to be disclosed. The next part is how to develop the exploit. I will leave the following time to my colleague, Dennis.
Thanks, Lance. I'm Dennis, and I will share the remaining part of our talk. First, when we have a new zero-day vulnerability, what difficulties do we still face? The VMware's hypervisors are closed source, which create many difficulties for both vulnerability discovery and explosion. Moreover, there is no publicly available exploit code and very few public exploit flows. What even more challenging is that the VMware places great importance on the security of its software. Almost all public exploit primitives are being patched, making it difficult to continue using historical exploit flows. Finally, due to the nature of VMware virtual machine software, only a small number of code paths can be fully controlled by who is in the guest OS, which greatly reduced the number of modules where exploit primitives may exist. Despite these challenges, we conduct further research and discovered a new set of generic exploit primitives that helps us achieving VM escapes. Before sharing this new explosion approach, let me first share some of the past exploit primitives and how VMware patched them. This slide lists multiple historical public exploit primitives and how VMware fixed them. But due to the time constraints, I will not go into detail. After searching and analyzing these historical exploit flows, we found that there was no exploit primitive that could be used directly. So we had to look for it ourselves. Fortunately, we finally find a new exploit object. This powerful Excalibur we find is URB, the object we mentioned earlier when analyzing the vulnerability. The URB USB request block is an universal object for transferring USB packets in VMware and is used by all virtual USB controllers. Since almost all virtual machine configurations include USB devices, this also means that the primitives built around it are very generic. The diagram on the right shows the data structures of the URB and its related objects. After our previous introduction to the vulnerability, I think there's no need to explain each member here in detail. However, there are two new objects that we haven't mentioned before. One is VUSB device, which VMware creates when each USB device is connected. It includes the pipe array of this device. The another object is DEV device. This object is located in the program's data segment and contains related function pointers. Therefore, we can see that URB is a very ideal exploit object. Firstly, it can be arbitrarily allocated and freed, and its size can also be arbitrarily controlled by us. Its members include a variable length data array, a member of control the length to read, the write-back length, a pointer to data, and a pointer to a pipe. Through the pipe pointer, we can index the device object and obtain the program space address. Next, I will explain in detail how we can use the URB and the related objects to construct exploit primitives and build our explosion approach step by step. First, we need to convert the out-of-bounds write vulnerability to an out-of-bounds read. We can arrange the memory according to the diagram on the right. I will introduce the memory grooming method at the end. First, allocate URB1 and URB2 and ensure they won't be fully processed and freed. This step requires the write-back length of this URB to have a value, and we don't use enqudd to read it back, so it will be reserved on the memory. The second step is to create an EHCI control transfer and allocate the URB in front of URB1. Then use the out-of-bounds write to override the write-back length of URB1. Once the write-back length of URB1 is overwritten, we can use URB1 to read more content, including the pipe address and buffer address in URB2. The next part is arbitrary address read. So it is very easy because we already have the heap address. We can just override the URB1's PURB data cursor to any location. The next step is arbitrary address write. Initially, I encountered difficulties here. Although we can modify the PURB data cursor of the URB to an arbitrary address, but once the URB is created and sent to the USB device, it cannot be written again by the system software. If we send a new transfer queue, it would naturally create a new URB instead of obtaining the original one. So how can we achieve arbitrary address write? I thought of pipes. We can modify the pipe pointer of the URB through an out-of-bounds write. Is there any write operation that can be performed through a pipe? I found this primitive in the UHCI check and write back function. The check and write back function is executed once before and after the transfer function to check the transfer status and write the return data from the USB device to the physical address in the guest. I found this primitive in UHCI, which is the USB 1 controller. Since a device is connected to the UHCI controller by default configuration, this can be triggered by default. The pipe parameter of the UHCI check and write back function comes from the URB pointer. We can see that the frame in the function comes from the pipe. More interestingly, the function writes the content of the 4 bytes pointed by the one pointer in the frame to another pointer in the frame. Since both frame and the pipe are forked by us, This allows us to perform a 4-byte arbitrary address write. This image, the image in the bottom right corner shows the assembly code for this line of C code. After achieving arbitrary address read and write, the next step is to find primitives to control the RIP. What kind of targets do we generally look for? A dynamically allocated object with a function pointer where we can invoke the call of the function pointer. The object closely related to URB is a pipe, fits this criterion. In the pipe release function, cancel pipe, the very first instruction is to call a function pointer from the VUSB device in pipe, and we can also control the first and second parameters. That is very great. If we can forge a pipe and trigger cancel pipe, we can achieve arbitrary code execution. In this regard, I found two approaches to utilize. Pass one is to, as we can see from the image, in the EHCI check and write back function, the pipes comes from the URB. Then, under certain condition, when EHCI check modified setup returns an error, it will execute cancel pipe. When we forge the pipe through an out-of-bounds write, we can achieve arbitrary address call. Sometimes we may not be able to use pass one. For example, in case of VMware Fusion, the default configuration uses a USB video device. In my attempts, I found it difficult to retain the EHCI URB, so I had to seek other ways. However, since we can achieve arbitrary address write, we can do more interesting things. For instance, we can directly write a forged pipe object into the pipe array of USB device. Then by triggering a port reset through the EHCI registers, it will call destroy all pipe and eventually release all pipes in the USB device, including our forged pipe. Finally, let's talk about the primitives required for heap grooming. This part is not our own finding, but comes from the content of the Black Hat Europe talk. Using the shader object in the SVJ model can help us complete heap spraying and grooming. It can be specified to any size and can be arbitrarily allocated and freed by us. The below are the commands requiring to allocate and freeze the shader object. For the more details about SVJ, I've also attached the link to the white paper of this talk. With sufficient primitives, our explosion becomes feasible. Here I share my actual explosion plan, which may seem complex because we chose the pass2 method to control RIP, which also requires us to leak more information. The good news is that after each EHCI control transfer is completed, the URB will be freed, and the next allocation will still be in this freed position. So there is no need to message the heap again. However, the actual explosion does not stop here. We still face a big problem. The problem comes from macOS itself. The macOS libmalloc uses magazines to manage heap blocks, which with each CPU core having a unique corresponding magazine. When a program executes malloc, the malloc finds the corresponding magazine to complete the heap trunk allocation based on the current CPU core of the process. This means that every time we allocate a heap trunk, the corresponding magazine and memory area are random. This causes a very big problem for us. And the diagram in the lower left shows the heap management of libmalloc. Therefore, we can find that the memory areas of the magazines corresponding to each CPU core are different, and the allocated heap trunks are not together at all. And the diagram on the right shows a simple experiment I did. I kept running malloc in the program and then counted which magazine the heap trunks were in. We can find certain patterns, such as most heap trunks being allocated in magazines with even-numbered indexes, which implies that CPU scheduling priorities even-numbered CPU cores. But the important point is that almost all magazines will be covered. We did some research on libmalloc and then come up with a way to deal with it. First, we can ensure that when we are using shader to spray the heap, the CPU core will not switch because they can be in a simple while loop, as long as we put the comments into the command pool at once. However, once there is a thread switch, such as from SVJ to EHCI controller, it is impossible to guarantee that it is still in the same CPU core. Therefore, if we cannot ensure that the EHCI control URB and the shader we arranged in advance are in the same magazines, the out-of-bounds write will cause the program to crash. But what if we do a heap layout in all of the magazines? Yes, this is the countermeasure we came up with. First, repeat the basic heap layout and try to have at least one complete layout in each magazine. Then, for each subsequent step of the operation, try a large number of times to ensure that our out-of-bounds write and the information that needs to be leaked happen to be in the same magazine. It doesn't matter if they are not in the same magazine because we have layouts in each magazine which will not cause crash. We just need to keep trying. At this point, we are left with the most important question: how to ensure that all magazines are laid out. We thought of many ways, such as adding a sleep between each round of allocation. We experimented with various sleep times from small to large, but unfortunately, none of them worked. When the sleep time reached more than 1 second, it actually ensured fewer magazines for heap spraying. This is understandable because from the previous slides, we can find that magazines with even-numbered indexes are more likely to be scheduled. Then we try to increase CPU's occupancy to increase CPU core switching, hoping to switch each CPU core more evenly. Unfortunately, this didn't work either. We speculate that it may be because what we can do is only increase CPU cores in the guest system of the hypervisor, which has too little impact on the host operating system. Finally, we explore two ways to increase the probability of success. The first is to remove sleep and speed up the explosion. CPU scheduling should be at milliseconds intervals, and the fast explosion can reduce other interferences. The second is to use a huge number of heap spraying rounds. The dozens or even hundreds of rounds are too few. We used more than 0x1000 rounds of heap spraying to ensure more comprehensive magazine coverage. We can directly use the basic heap layout to spray heap without allocating many useless shaders before the layout, because if it is an odd-numbered index magazine, there are actually fewer heap chunks on it, and it doesn't need much heap spraying. Direct heap layout can succeed. Eventually, after a long time of debugging, we increased the success rate on a MacBook Pro 13 to over 18%. This may still not be perfect, but due to the randomness of magazines, we are quite satisfied with this result, and we also complete the escape on the first attempt at GitHub 2022. Next, let me play a demo which records our VMware Fusion virtual machine escape attack. So this is a VMware Fusion, and first we check the version of the macOS and the version of the Fusion. The guest is the Ubuntu, and this is our exploit. We just run the exploit, and it will pop up the calculator. Yeah, that's it. Thank you. Okay. Then let's briefly share the exploit of VMware Workstation. It should be noted that under this default configuration, there will be no devices connected to the EHCI controller. Therefore, to trigger the vulnerability, we need to manually connect a USB device to the EHCI controller. The explosion on Windows will also face some troubles, such as LFH, the lower fragment heap. The existence of LFH increases the difficulty of explosion because it randomly allocates heap trunks. Fortunately, the primitives we use, including URB and shader, can exceed 0x4000, which is the maximum size of LFH. This makes heap arrangement much easier. For the objects that cannot be larger than 0x4000, we can choose a size that has not yet been enabled by LFH, such as 0x370. The image in the lower left reveals how we complete out-of-bounds reading under the Windows. The final explosion idea will be as shown in the lower right corner. And this is a demo of escaping on workstation. And we just record the same thing and run the exploit. And how about the calculator? The last explosion case is on VMware EHCI. Like workstation, no default devices on the EHCI controller. For the EHCI, it is a system similar to CentOS 7 using a very old glibc version 2.17. However, in the new EHCI 8.02, it has been updated to version 2.28, the same as CentOS 8. So the explosion idea on EHCI will be similar to that of Fusion, and we don't need to face the randomness problem caused by the magazines. So at this point, it will be easier. Another difference is that since 3D graphics acceleration is not being enabled by default in EHCI, we cannot use the shader object. We can use GMR instead. Although it cannot be allocated in large quantities like shaders, it still has a high degree of flexibility. Due to the length of this talk, I will not go in details about the related explosion here. We completed VMware EHCI VM Escape at the 2023 Tianfu Cup and eventually gained the highest privileges of EHCI. I hope we will have opportunity to share more in the future. And the last part is the takeaways. First is, where bugs have arisen with similar software, there may be new bugs. The second is, when looking for exploit primitives, try to look for objects related to the vulnerability. The first time, I first do reverse engineering in lots of other modules, but I can't find the good objects. But when I look back to the vulnerability, I found the URB is really powerful. The last is virtual devices, especially USB-related devices, are now a popular attack surface. So this is our talk. Is there any questions here? You can ask us after the presentation. Okay, so this is our talk. Thanks for listening and hope you like it.